This video is about the key component in a capacitance scanner, which is an integrator. So capacitance scanners can work because the capacitance of a ridge of your fingertip differs from the capacitance of a valley of your fingertip. That's because if you can imagine the extra pocket of air that you get in a valley, that adds to the insulation of the capacitor and you get a lower capacitance. So if you can see where the higher and lower capacitance are coming from, then you can build an image of the fingerprint. So in an integrator, if you change the capacitance of the integrator, you change the voltage out that you get. And analysing that voltage will tell you whether your signal has come from a valley or whether your signal has come from a ridge. And in the next video, I'm going to actually build an integrator. But for now, I'd just like to take you through the theory of how it works. So we'll start with the setup. This is an op amp. And there is a V out here. And a V in here. And as V comes in here, there is a resistor, R1. And for argument's sake, we'll give this a value of 1 kilo ohm. Then there's a wire up here, goes to a capacitor, and comes down here like this. Okay, now the first thing to note is that there is a point here of 0 potential. Now that is because it is a golden rule of op amps that you are not allowed any current to go into the op amp. So the current coming in here, I in, it can't go this way, so it all has to go this way. We'll call this IC. The C is for the fact that the current is going through the capacitor. So let's write that down. So I in must equal IC. But what is I in? So I in is V in minus 0, the potential across the first part of the circuit, over R1. And what is IC? Well, if you recall that for a capacitor, Q equals VC, where Q is charge, then dQ by dt, which is current, will equal dV by dt C. So that is equal to IC. Now, both of these things are equal to one another, so let's equate them. So we've got dV by dt C equals V in over R1. Great, now what is this V here? Well, it's the potential across the capacitor, which is 0 minus V out. So plugging that in, we've got d V out minus by dt C equals V in over R1. I'm not bothered to include the 0 volts bit because obviously that would equal 0. So if we rearrange this and integrate, we get dt over here, V in over R1C equals V out, stick the minus sign there. And this is the equation for our integrator. So let's think about what that would do to our input wave. So the first thing to note here is that obviously our V out is going to be an integrated version of our V in. So imagine that our V in was a sine wave. then our V out would be a cosine. Or if our V in was a square wave, like this, then our V out would be like this. I don't know, like this. And so on. So it's an integrated form of the input wave. The second thing to note is that V out has a dependency of 1 over C. Okay, so this means that in my next video I'm going to use two capacitors. One is going to be 0.01 microfarads and one is going to be 0.1 microfarads. And the bigger the capacitor means the smaller the gain for V out. So if I take this one, I would imagine it to have 10 times the gain of this capacitor. And hopefully you'll be able to see that in the signals in the second video. And gain just means that the voltage has been multiplied by that much. So if you had a wave like this as your input, and then it was suddenly 10 times that big, it would be like this. Okay, so that's it in theory, but there's a problem in real life, and the problem is to do with saturation. So when you apply a gain to these voltages, obviously then you get out a bigger voltage at the end, but you can't get a bigger voltage than your supply voltage. So you have to supply your circuit with power. And if you've picked, say, a 15 DC supply, it means that whatever gain you apply to your V in cannot exceed 15 DC. So how does that work with integrators? Well, the impedance of a circuit is 1 over omega C, which equals 1 over 2 pi FC. And now the gain of our circuit in terms of the impedance is V out over V in, which equals minus XC over R1, which using this formula equals 1 over 2 pi FC R1. So if we plot the gain against frequency on a graph, we get a line like this. And that is because the gain is inversely proportional to the frequency. Now, the problem with this is if you're working at lower frequencies over here, the gain is so high, and that means that the wave will saturate. So the voltage that you get out of the circuit will be higher than the voltage that you've supplied the circuit with. And if it's higher than the voltage you've supplied the circuit with, the saturation causes a distortion in the wave, so you can't get the information out of it that you need. So you may say, okay, well that's at lower frequencies, so what if we work at a higher frequency, then will we get rid of the saturation? And the answer is, unfortunately, there's an offset input voltage, which is also amplified through the circuit, which will cause the circuit to saturate anyway. So in order to get rid of that saturation, what do? Well, fortunately, there's a simple solution, and it's to add another resistor to our circuit. The resistor we're going to add, we're going to call R2, and we're going to put it in parallel with the capacitor. Okay, so this is R2, and it's going to have a resistance of 100 kilo ohms. So let's take another look at our gain frequency plot. So So what adding the resistor to the circuit has done has meant that at lower frequencies, the circuit will now work as an inverting op-amp. And if you want some information about inverting op-amps, please have a look at the link below. But it means for higher frequencies past a certain threshold, it will return to working as an integrator, but without any saturation, so you get a clear signal. Okay, and what is that threshold frequency? Well, let's say it's here somewhere. Let's call it FC. And FC is given by 1 over 2 pi R2C. So frequencies past this frequency, it should start to work as an integrator, but if you build an integrator practically, you're looking to put an input signal frequency that is about 10 times bigger than FC. So hopefully from that explanation, you get an understanding of the kind of circuit that we're trying to build and what we're expecting to see from that circuit. So if you wish to, you can watch the next video on building the integrator to actually see that in action. Thanks for watching.